In section 8.2, there's only one main idea in this problem. There's one big idea, one small idea, and an application. But the hard part is you just have to practice to get better at it. Okay, so there's choices to be made, and sometimes it's not obvious what choice to use. So this is called integration by parts. Now, this whole chapter is on methods of integration. So anytime you have an integration problem, you're going to have to ask yourself first, is it straight integration? Can you just write down the answer or do a linear substitution? The second thing then, is it a substitution problem that you covered in Calc 1? So straight integration, substitution. Then you're going to ask yourself, is it an integration by parts problem? So you need to, as we go through this chapter, you need to learn, the methods and make sure you can rattle them all off. I can't tell you how many times on a test a student said, I couldn't figure out how to do that problem. Well, what methods of integration do we have? And they couldn't mention the one that it was. So that's the problem. It didn't occur to them to check that one. So make sure you can rattle through all the methods. So this is called integration by parts. So I want to just briefly explain where the formula comes from. So suppose you had u and v. So u is something with x's in it, and v is stuff with x's in it. I mean, let me just make something up so you can see the notation here. Suppose u was x cubed, and v was tangent x. I'm just making something up. All right? And suppose we wanted to take the derivative of x cubed tan x. This example is not the notes, don't worry about it. Okay? So, well, it'd be a product rule, right? It's a product, so you have to use product rule. So it'll be the first derivative of the second plus the second derivative of the first, right? No problem. We know how to do derivatives with product rule. Okay, so let me rewrite it in terms of the notation they're using here. Okay? So going back to u's and v's, that's uv. Right? This is u, and this is dv dx plus v du dx. So that's the very first line there, right? So u and v have x's in it, we just don't know what they are. So how would you take the derivative? It'd be first derivative of the second plus second derivative of the first. No problem. No problem. Okay? So suppose you started with this line here, or this line here. If we integrated this, let's integrate both sides of this with respect to x. Well, this says take the derivative of that. Well, if you anti-differentiate, you're just going to go back to what you started with. So this would just be x cubed tan x or uv. My u's typically have a tail on them, my v's do not. Okay? So now this we don't know how to integrate, but that'd be the integral, and I'm going to stick to their notation, of u. Now since we're integrating, you need to put the variable out here you're integrating with respect to. I mean, that'd be dx, right? Again, x's are hidden in the u, and x's are hidden in the dv, x's are in the v, and x's are in the u. So we're integrating with respect to x, okay? Now, in terms of this expression right here, they're just writing this as v prime instead of dv dx. And then plus the integral of v, and then this is u prime dx. So that's where that next line is coming from. So think about what this line is saying, right? It says x cubed tan x would be the integral of x cubed secant squared x plus the integral of tan x 3x squared. And then just as a notational sort of thing here, okay, they're rewriting this as u, instead of v prime dx, they're just writing dv. So realize when you say dv, we're integrating with respect to x, but the dx is hidden in the dv. So whenever you see dv, you're thinking of, it's the derivative of v, but then you also have, the dx out there. So then this is integral of v du. Okay, so that's just a shorthand notation. So you don't have to think v prime dx. All right, let me write this again. So we have uv is the integral of u dv plus the integral of v du. That's where we are. Okay, let me erase all. But that's usually not the way we use integration by parts. Let me just solve for integral of u dv. So the integral of u dv, if you subtract this piece, this integral from both sides, you get uv minus the integral of v. So just subtract this integral from both sides. So the integral of u dv is uv minus that. So this is the integration by parts thing. Okay? Now what does integration by parts do? Okay? Integration by parts helps you integrate products. So suppose you have an integral with a product, a u and a dv. Remember, dv has x's in it, u has x's in it. So you don't know how to integrate this product. Maybe it's something very, very complicated. Well, this tells you if you can't integrate it this way, if you can rewrite this in this way, maybe you can integrate this. So maybe u dv is complicated, but v du is easier to do. So that's the game, okay? And then notice there's no integral sign here. This is just u and v, okay? So whatever u is goes here. If this is dv, you have to figure out v, so you have to integrate. And notice if you have u here, you take the derivative of u here. Okay? So you'll see as we go through examples of the idea. Let's do an easy one first. So the first one says evaluate the integral of x sine x dx. Okay, so the first thing you ask yourself is this a straight integration problem? Okay, just because a problem is in section 8.2 doesn't mean it's an integration by parts problem. They purposely in the homework are putting problems that are just basic substitution problems or straight integration problems to make you run through the checklist. Now, no, I don't know the answer to this. Now, what about just a basic substitution? The only logical thing to try would be u is sine x, but du is cosine x. There's no cosine x for you. Right? Or let u be the whole thing, but du would be a big mess. Okay, so I've eliminated all the stuff we've done before. Now, what about an integration by parts problem? It is a product, okay? Now, the thing is, it's written in this order. That doesn't mean u has to be x and dv has to be sine x. Remember, the game is, whatever you pick for u, du winds up in the integral over here. Right? And we want this to be simpler. So you want to pick something for u that when you take the derivative, hopefully becomes simpler. And whatever you pick for dv, v goes here. So whatever you choose for dv, you have to find the antiderivative to get v. So typically you want to find whatever you choose for dv, when you integrate that to get v, it'd be nice to be easier, but typically you don't want it any worse. The integration, typically when you integrate a function, usually the function you get is more complicated. So I usually look for u's that when I take the derivative it gets simpler, and when I choose dv, when I integrate, it gets no worse. So then this integral is simpler to do than this one. So with that in mind, I'm going to let u be x, and I'm going to let dv be sine x dx. So this is my u, and that's dv. Now whatever you choose for u and dv, make sure the product is actually your original product, okay? Make sure your product is your original product. So u dv, the product, is my original product. Well, I'm going to go ahead and figure out what du and v would be. So du, well, if u is x, dv is 1 dx. And if dv, the derivative, is sine x dx, what is v going to be? Well, what's the antiderivative of sine x? It's negative cosine x. Sorry, my computer's making noise. Now, I like to write it this way. Some people like to put u du and v dv or whatever. I like to put u dv here because that's my original problem. Notice this is v du, which is my integral over here. So that product is that integral, and that product is that integral. I just like to do it that way. Okay, so let me go back to my original problem here. So the integral of x sine x dx, that's my u dv, that's equal to uv, that product, minus x cosine x, uv, minus the integral of the v du, and that's minus cosine x. And notice the original problem I couldn't integrate, but this one I can. It's very easy. So let's just finish this one up. Now this is a plus, okay? So I'm really integrating cosine x plus cosine x. And that turns out to be sine x. And don't forget your plus c for the indefinite integral. So that one's not that bad. That one's not bad. Now, if you want to check another way, you can always take a derivative. What if I take the derivative? I mean, I'm done with the problem, but just to show you. What if I took the derivative, just to show you why this works, of this? The derivative of this should be x sine x. Well, you have to use product rule here. When I have a constant out front and a product rule, I always group it with the first term. That's just what I like to do. So first, negative x. Derivative of the second is negative sine x. Plus the second cosine x times the derivative of the first is minus 1. And the derivative of sine x is cosine x. And notice those drop out, and this becomes x sine x, which is what I wanted it to be. So you see what happens. When you do the product rule here, you wind up getting a term here that drops out with that one here. Okay, so that's the first example, not bad. Okay, notice the hard part is figuring out what's u and what's dv. Right? Okay, the next one says, oh, integral of natural log of x dx. Oh, that seems so simple. Haven't we done that before somewhere in this course, or in Calc 1? No, you never learned how to integrate. We know the derivative of natural log. The derivative of natural log of x dx is 1 over x. Okay? We never did the integral of natural log because we didn't have integration by parts. Now here you may say, well, wait a minute, it's just natural log of x, there's no product. Sure there is. You can always add in a 1. Okay? Now, it makes no sense here. Right? If you, okay, don't write this down yet. If you write dv as natural log of x dx, you know, if you choose that for dv, what's v going to be? Well, to figure out v, you have to find the antiderivative of natural log. If we already knew that, we wouldn't have to do parts. Right? So keep that in mind. If you pick something for dv, make sure it's something you can integrate. We can't integrate that, so that doesn't help. Right? So u and dv. So u will let u be natural log of x, and dv is just 1 dx. If you want to put the 1 there, you can. Okay? So does everybody understand? So the natural log of x here, making that dv makes no sense, because if I could find v, I could have already integrated and given the answer. I notice natural log of x times 1 dx is the original interval. Okay, so we need to find the du. Well, natural log of x, the derivative is 1 over x dx. And then what's v? Well, if dv is 1 dx, v is just x. Okay? So let me write the original form. Integral of natural log of x dx. That's u v, so that's x natural log of x, minus the integral of v du. Well, what's 1 over x times x? That's just 1. And notice this integral is a whole lot easier to do than the original, because we didn't know how to do the original. And so you get x natural log of x. The integral of 1 is just x. So there's the integral of natural log of x. We've finally seen the integral of natural log of x. And again, just for kicks, just to check my work here, let me take the derivative of my x natural log of x minus x. The derivative of that should be natural log of x. So if you use product rule on the first part, it's first derivative of the second, x times 1 over x, plus the second times the derivative of the first, which is 1, and then the derivative of minus x is minus 1. And notice again, one of the expressions that turns out in your product rule subtracts out with that, just like it did in the previous checking. And there we go. So this is a standard problem, and integration by parts, because it's a common function that you never learned how to integrate. But now you know how to integrate. You don't have to memorize this answer. I will just have to look it up. Okay, so there's 2 problems with integration by parts. Okay, the third one says the integral of e to the 2x cosine 2x dx. Now this is one of my favorite types of problems. When I first saw this, when I had calc years ago, I was just so impressed with the method. Okay, so straight integration, no, I don't know the answer. And substitution, well, if you let u be e to the 2x, du will have an e to the 2x, but how are you going to get cosine in terms of e's? You let u be cosine, du has a sign, but there's no sign, and how are you going to involve the e? So it's not looking very promising. Now, what about an integration by parts problem? Well, there is a product. Right? Notice the previous one, the natural log of x, it wasn't obvious it was integration by parts because it wasn't a product. You had to insert the one, so keep that in mind. If you're just desperate and you don't know what else to do, you can always try integration by parts by letting u be the integrand you have and letting dx be the dv. Okay, so let's try parts on this. So we need to identify a u and we want to identify a dv. And the product has to be this. Well, it makes sense to let one of them be e to the 2x and one to be cosine 2x. Now, which one? Now, remember, I told you when you set this up, when you pick u, when you take the derivative, you'd like for it to get easier. If u is e to the 2x, the derivative is going to involve an e to the 2x. So it didn't get easier, but it didn't get worse. And if u is cosine 2x, your du is going to have a sign in it, which is no worse than cosine. So your derivatives don't necessarily get easier, but they don't get worse. Now, what about dv? If you let dv be e to the 2x, well, the integral is going to involve an e to the 2x. If you let dv be cosine 2x, the integral is going to involve sine 2x. So in this problem, it doesn't matter, right? At this point, you think, well, you know, neither one of the factors gets easier when you differentiate or integrate. So so I don't have to deal with a bunch of fractions, I'm going to let u be e to the 2x and dv be cosine 2x. Well, I guess it doesn't matter. I'm going to fraction either way. Yeah. So it really doesn't matter. Okay? Now let's figure out du. So if u is e to the 2x, you have to use chain rule. The derivative of e to the stuff is e to the stuff times the derivative of the stuff. Now what's v here? Now, this is a linear substitution, right? If you were integrating cosine 2x, you would let u. Now be careful. The u here is the integration by parts u, not a u substitution u. Okay, so be careful. So if you let u be 2x, that would be a linear substitution. You know the integral of cosine is x. Cosine x is sine x. So the integral of cosine of linear will be sine of linear, but then you have to adjust for the slope, so 1/2. Right? Because the derivative of sine of 2x is cosine 2x times 2 times the half will give you 1 up. And I'm writing way too big because this problem is kind of long. Okay, so now you have to be organized when you do a problem like this. And all your integration by parts problems, you have to be organized. This is why I write everything out. I'm going to go ahead and do it up here so then I can erase that and give myself more room. So my original problem integral is uv, so 1/2 e to the 2x sine 2x minus the integral of that product. Oh good, the fractions drop out anyway. Right? So that product, the 1/2 of 2 is 1, so I get e to the 2x sine 2x dx. Okay? So my original integral is uv minus the integral of that product. The 1/2 and the 2 drop out. Okay, good. Okay? Okay, so we changed our original integral into another one. And you think, well, it's no worse, but I don't know how to do this one either. All right? See, that's the problem, because neither factor got easier over here. It's the same level of difficulty. I can't just write down the answer to that one either. Well, why don't we try integration by parts again? Let me get another marker. Okay, let's do integration by parts again on this part. So I need a u, a dv, a du, and a v. So notice this is not an integral, so that's done. Now you have to be careful here. If you have to be consistent. If you're going to do what we did, then do it again. I let u have the e and the dv have the trig function. You need to stick to that, because if you don't, you're going to undo what you did, and you're going to wind up with integral of e to the 2x cosine x equals the integral of e to the x, e to the 2x cosine 2x. So you don't get anywhere. So don't undo what you already did. So with that in mind, I'm just going to stick with u is e to the 2x, and dv is sine 2x dx, right? If you had let u in the original part be cosine, you would let u be the sine here. Okay, well what's du? The derivative of e of the stuff is e of the stuff times the derivative of stuff dx. That's a chain rule. And now if dv is sine 2x, the integral is going to be minus cosine. It's a linear substitution again. So the integral of sine x is negative cosine x. So the integral of sine of linear is going to be minus cosine of the linear, minus cosine 2x. But then you have to adjust for the slope, 1/2. Okay? So now we're ready to go. Now, here's what I'm saying about being organized. I'm not just going to start writing one piece of this. I'm going to continue. Well, let me just write the whole thing again. I have the integral of e to the 2x cosine 2x dx is 1/2 e to the 2x sine 2x. That's what I have here. Minus, and now I'm going to do integration by parts on that integral. But I'm writing everything out. Because I have students that they'll just focus on that. They never go back and pick that up again. Plus, it's a mess when you do that. You need to be writing out full steps. Okay, so this integral is uv minus 1/2 e to the 2x cosine 2x, that times that, minus the integral of that product. Remember, that product was my original integral, so my new integral is that. So I have negative 1/2 and 2, so that's negative e to the 2x cosine 2x dx. Okay, let's clean this up a little bit. Again, I'm going to start writing here. 1/2 e to the 2x sine 2x. I have to distribute this minus sign. That becomes a plus 1/2 e to the 2x cosine 2x. Now be careful here. That's minus minus, which becomes a plus, but then you have a negative out here. So this is minus the integral of e to the 2x cosine 2x dx. Okay, there. Now that looks a lot better. Okay? Well, wait a minute. We're back to our original problem. So we did integration by parts twice, and we got back to the original problem. Well, that kind of stinks, doesn't it? Well, okay, let's look and see what we have for a second. Where we are. So we cycled back around to our original problem. Well, suppose I gave you, okay, don't write this down. This is just so you can visualize, because this is a big mess. Suppose I had b equals c plus d minus b. Oh, here, let me change that c plus d. Let me just put a 8. And I said solve for b. Couldn't you solve that equation for b? It's a linear equation, right? It's b to the first, b to the first. Right? You would just add b to both sides. You get 2b is 8, and then b is 4. It's very easy. It's very easy, right? Think about what we have here. What are we trying to solve? We were trying to find the integral of e to the x cosine 2x, right? That's what we're trying to find. We're trying to find this. But notice it also showed up here. Right? Think about what I have here. What I'm looking for is what I call b. I have b is 8, something, minus b. So what we have here is a linear equation where the variable is the integral of e to the 2x cosine 2x dx, right? So let me write it down here just so we have it. E to the 2x cosine 2x dx. Right? I'm trying to solve for that, and it's on both sides of the equation, just like this one is. Right? So what am I going to do? I'm going to add that integral to both sides. So if I add the integral of e to the 2x cosine x dx to itself, I get 2 of them, just like I did there, 2b, is going to be that. Now technically, there's one little thing we have to talk about here. But hopefully you understand that step. So whenever you do an integration by parts like this, and you do it once, and you do it again, or a third time even, and you go back to what you started with, treat it as an equation, right? And that's the variable you're trying to solve for. So again, I've added this to both sides of the equation, so I got two of those, and then this one is gone. Now technically what I've written here is not, the math is fine, but notation-wise we have a problem. Because notice over here, I have 2 times an indefinite integral. And notice over here I have a function. But remember, what's the definition of an indefinite integral? It's the set of all antiderivatives of the integrand. I have one of them. So at this point, you need to put your plus c. Now, why didn't I worry about a plus c here? Because I have an integral here, the plus c is built in. I have an integral here, the plus c is built into the integral. But as soon as I move that one over, I don't have an integral over here, I just had a single function. Okay, so that's why you need your plus c. So how do we solve for integral of e to the 2x cosine 2x dx? Just multiply both sides by half. All right, to get rid of the 2. So a half of that is 1/4 e to the 2x sine 2x. Half of this is 1/4 e to the 2x cosine 2x. And if you take half of a constant, you have another constant. So you don't have to put half c, you can just say c. I think that's so clever, this solution. Okay, so that's another example of integration by parts here. Okay, let's do another example. This is the integral of, from 0 to 1 of x, arc sine x squared dx. Okay. Okay, straight integration? No. You got arc sine of stuff and you have a product, probably not. What about a substitution? Well, if you let u be x squared, du is 2x, and there's an x waiting for you, so it looks like it may be a substitution problem. The problem is, when you do the substitution, you're going to get arc sine u, and we don't know how to integrate arc sine. We know the derivative of arc sine x, but we don't know the integral. So with that in mind, that should be a dead giveaway that when you do integration, when you try integration by parts, arc sine of x squared is not going to be dv because we don't know how to integrate it. Okay, so we need to choose the u, we need to choose the dv. So for u, we're going to choose arc sine of x squared, and for dv, we're going to do x dx. Remember, the product of these two needs to be your original product, your integrand, and it is. Okay, so we need to do du, and we need to do v. Now let's do the v. Well, if dv is x, then v is x squared over 2, isn't it? Now notice here, my integral got more complicated. We usually like that to be no worse. But again, we couldn't have chosen dv to be arc sine because we don't know how to integrate arc sine. So we didn't have a choice. So this makes sense to try this. But if u is arc sine of x squared, what's du? Well, what's the derivative of arc sine x, first of all? You remember, you should, right? It's 1 over the square root of 1 minus x squared, right? That's the derivative of arc sine, right? So, but this is chain rule, right? It's not arc sine x, it's arc sine x squared. So the derivative is 1 over the square root of 1 minus x squared squared, which is x to the 4th, and then times the derivative of the stuff, which is 2x. Right? The derivative of arc sine x is 1 over square root of 1 minus x squared. So the derivative of arc sine of stuff is 1 over the square root of 1 minus stuff squared, so x squared squared, times the derivative of the stuff. Okay, so we have that. Okay, so now let's do our integration by parts here. So the integral from 0 to 1 of x arc sine x squared dx is, well, it's uv. So x squared over 2 arc sine x squared minus the integral of that product. Well, the 2's cancel, and you get x cubed over the square root of 1 minus x to the 4th. The 2's cancel x, yes. So even though the integral got a little bit worse, notice the derivative got a lot better. You may say it's worse, but we got rid of arc sine, right? We got rid of the arc sine and we're back to roots. Okay, now again, what I've written here is not a true statement. Notice on the left-hand side, this is a definite integral. I have a function and an indefinite integral. So you still need the limits of integration here. And on this part, I mean, that's why we have to, I had to do an example of the definite integral, right? Remember, a definite integral, if it exists, is a number. This is not a number, it's a function. You have to evaluate that from 0 to 1. Okay? So we have to evaluate that to get a number. And then we have to finish by integrating that. Okay. Why don't I, let's just go ahead and evaluate that and worry about that in a minute. So if I plug in 1, I get 1/2 arc sine of 1 squared, arc sine 1, and then minus 0. And plug in 0 here, you get 0. Now what's arc sine 1? Okay. Remember arc sine, right? When you say, you know, arc sine of 1, remember that's an angle. 1 is arc sine of a number is an angle. If I say arc sine of 1 is theta, what does that mean? That means sine of theta is 1, and theta is either 0 to pi over 2 or minus pi over 2 to 0. Remember, arc sine lives in these two quadrants with this direction, with that rotation, either up or down. Right. Well, that's a quadrantal angle, isn't it? Right. Remember, sine of, the maximum sine can be is 1. That's not a quadrantal. That's 1, 0, 0 minus 1, and 0, 1. When we use the unit circle, sine, cosine is the x value, sine is the second value. So sine is here. Yeah. So that's pi over 2. So this turns out to be half of pi over 2, which is pi over 4. Again, that's from your pre-calc class. If you are rusty, you need to go back and review that. Okay, so we're done with that. I don't need this. Anything that we talk about that you're like, wait, I don't remember that, if it's from pre-calc or calc 1, you've got to go back and review. I highly recommend, I mean, your book you can use for calc 1 review, but if you don't have a pre-calc book, go get on Amazon or somewhere and just find an old edition. You don't need the last edition of a book. You know, find an old edition of the book that you used in pre-calc and it'll cost you $5. Okay, so now we need to do this integral right here. That's all that's left. Just for notational purpose, well, I guess it's all right. Okay, so now what about this integral? Straight integration? No, probably not. It's a big mess. Might have a root, have a quotient. Now what about a basic substitution? I think we're in business there. If you let u be 1 minus x to the 4th, du is going to be minus 4x cubed, and there's your cube waiting for you. Okay? And even though I don't think it would confuse you, I'm not going to use the letter u just because we already used it in the parts. So I'm going to use w. So let w be the radicand here, 1 minus x to the 4th. And then dw is minus 4x cubed dx. Now I don't have a minus 4 here, so I'm going to just flip. So minus the 4th dw is x cubed dx. Let me check myself. W is that'd be minus 4x cubed. That's right. Okay, so now I'm going to pick up from here again. Equals pi over 4. So this is my original integral is equal to this, which is equal to pi over 4 minus x, substitute for that first, x cubed dx. X cubed dx is minus a 4th, so that minus is making like plus. Sorry. So x cubed dx becomes minus a 4th. I didn't put the 4th. Minus the 4th. dw. Notice it doesn't hurt to double check yourself. So instead of x cubed dx, I have minus a 4th dw. And now what's left, all I have left is the denominator, which is 1 over the square root of 1 minus x to the 4th. So that's 1 over the square root of w, or w to the minus 1/2. 1 over the square root of w is w to the minus 1/2. Now, there's a definite integral, so I need endpoints. Now again, don't write 0 and 1. Those were the endpoints for x. We need endpoints for w. But if x is 0, w is 1. And if x is 1, w is 0. Notice this is interesting. You know, the endpoints wound up switching, right? The smaller number wound up becoming the bigger number, and the bigger number became the smaller number. Okay, so now we just need to integrate pi over 4 plus 1/4. Well, what's the integral of w to the 1/2? Add 1 to the exponent, divide by the exponent. So you get w to the 1/2 divided by 1/2, which is multiplied by 2. And we're valuing from 1 to 0. Now, if you want, if it bothers you to have the smaller number on top, remember, you can always change the endpoints and then put a negative sign out front if you want. Normally I do, but always plug in the top number first, whether it's the biggest or bigger or smaller. Okay, so let me see, I have pi over 4 plus 1/2 of, if I plug in 0, I get 0, and if I plug in 1, I get 2. Oh no, sorry, I did the half already. And so when you simplify, you get pi over 4 minus 1/2, and that's the answer. Whew, that'll take a little bit of work. It's not too difficult, but it's very tedious. Okay. Now let's do another one. All right, now this is an example from the text itself. This is example 5, page 527. Again, normally I don't do examples out of the text, but this is a standard example that we just need to do. Secant cube x dx. Okay, straight integration, no, I don't know that formula. And substitution, the logical thing would let u be secant x, but du is secant x tan x, and there's no tan x up there, so that doesn't help you. Okay, so then what's the next thing? If it's not straight integration, not substitution, the next thing on your list should be integration by parts. So we need to choose a u, and we need to choose a dv. On this problem, the integration is not so difficult, but the technique to get to where we need to be, we have to do some little trickery. Now, what do you think about this one? Well, you can let u be secant cubed, and dv could be 1. But you could break up the secant cubed into a secant x or secant squared. Right? Now we can take the derivative of secant cubed or secant squared or secant, but now you have to be careful with the integration. It doesn't make sense to put secant cubed there, because if we knew how to go find v and integrate, we could just answer the question. So it doesn't make sense to put secant cubed here. What if we put the secant squared? Remember, the idea is that when you integrate, you want to get something easier or no worse. Do we know how to integrate secant squared? Well, sure. If dv is secant squared, v is tangent, isn't it? The derivative of tangent x is secant squared x. So that's a reason to put that here. Notice our integral got easier. We don't have a squared trig function, we just have a single trig function. So if I do that, then u is just going to be secant x, right? Because that product has to be secant cubed. And then du, the derivative of secant x, is secant x tan x dx. Okay, well that's not too bad. Now, I went ahead and just kept going because that made sense. Secant squared, tangent x, no problem. What if we had let u be secant squared, and then let dv be secant, switch them? Well, the derivative of secant squared, you have to use the chain rule, so it would be a little messier than this. Notice our derivative got messier, but our integral got easier. So on balance, notice but what if dv had been secant x? Then v would have been natural log absolute value of secant x plus tan x, and that would have gotten a whole lot worse. Right? So I think on balance, this, these two over here is a lot easier than, the derivative of secant squared, which would be a messier, and the natural log absolute value of secant x plus tan x. That's a lot messier, so this is the way to go. So I have the integral of secant cubed x dx is uv secant x tan x minus the integral of that, which is secant x tan squared x dx. So we didn't get any worse off, because if you think of this is a trig function to the third power. We have a trig function times a trig function times a trig function. So third power, degree 3. So we didn't get any, it's no worse. Okay, now you say, well, how are we supposed to do this? Now this is one we don't have to do parts on. Again, what you do here, again, write out all your steps. I'm going to use a trig identity. Remember, that was one of the, in section 8.1, that was one of the things in the chart, using a trig identity. Let's rewrite tangent squared as secant squared x minus 1. Because there's secant, well, right? Tangent squared is secant squared x minus 1. So if I break that integral up now, so I'm going to distribute the secant x and then break up the integral. So notice I have a secant cubed x here. So we're going to have minus the integral of secant cubed x dx. And then here you're going to have minus secant x, but with the minus there it becomes plus the integral of secant x dx. See, it's not so obvious to do that here. That's why I'm doing this example. Right? But notice what we get here. We get an integral we know how to do, and we're back to our original problem again. And we already did one like that where you wound up with the original problem. Notice this one wasn't do integration by parts and it cycles back to the original. We used a trig identity and we got back to the original. Okay, let me, I'm going to start again. So this integral is secant x tan x minus the integral of secant cubed x dx. That's this. And now let's go ahead and integrate this. The integral of secant is natural log absolute value of secant x plus tan x. Notice I don't need the plus c because it's still built into this integral. If you want to put the plus c, it's not wrong. It's just unnecessary. Okay? So I recopied that. The integral of secant x is that. Okay, so we're almost done. Now, we're trying to solve for integral of secant x, secant cubed x. I've got it on both sides again. Treat this as an equation where that's your variable. So let's add one of these integrals to both sides. So if I add it here, I'll have two of them. And then over here you'll have secant x tan x plus natural log absolute value of secant x plus tan x. Now I need my plus c, right? Because I don't have an integral over here anymore, the integral sign. So I just added integral of secant cubed x to both sides. So that's 0, and I have two of those. And now divide both sides by 2, and we've got our integral of secant cubed. So I'm taking a half. So 1/2 secant x tan x plus 1/2 natural log of secant x plus tan x. And a half of c is still a constant, so you can just write c. So that one's not too bad. But knowing to use a trig identity there, it's not obvious. Okay, so the last example in this section is using the tabular method. And I want you to notice at the top of the notes, under the where it says homework problems, on homework problems, only use the tabular method on problems that specifically say to do so. Right? Some of the problems we did, we could use tabular method on, but I want you to practice using integration by parts and writing everything out. If the problem on the homework says use the tabular method, use the tabular method. If it doesn't specify tabular method, I don't want you using tabular method. Okay, because I want you to practice what we just did. Okay, so as an example of tabular method, let's do the integral of x to the 4th sine x dx. Now okay, let's go through this. Straight integration, no. Substitution, let u be sine, there's no cosine. If you let u be that, how are you going to write that sign in terms of that? So it's not looking promising. Now what about, why is this a good integration by parts problem? It's a product. If you let u be x to the 4th, du becomes a cube. You do it again, you get a quadratic. Do it again, you'll get a linear. Do it again, you'll get a constant. Right? So the idea, a standard integration by parts problem is one of the factors when you integrate, you get no worse because you're going to get cosines and sines and cosines and sines. But when you let that be u, right, if that's dv, let that be u, when you keep doing integration by parts, the power gets smaller. So eventually you'll get down to a constant times the trig function, which you can integrate. Okay? So I think you'll see this requires several iterations of the integration by parts, because if u is x cubed and dv, u is x to the fourth and dv is sine x dx. When you do the first iteration, you're going to have an x cubed and a cosine. Then you're going to have to do it again. You're going to have an x squared and a sine. Then do it again. You're going to have an x and a cosine if I didn't lose my place. Okay, so this is perfect for tabular method. Tabular method is really nice when one of the factors, when you keep taking derivatives, you get down to zero eventually. Okay, so I'm going to write x to the fourth here. I'm going to write sine x here. I'm making a table. So it makes sense for that to be the u for the reason I said before. So let's just take derivatives down, right? So this would be u, du would be 4x cubed. But then if you did integration by parts again, this would be your u, so then du would be 12x squared. And then do it again, that would be your u, you get 24x. And then another one, 24, and then you're going to get a 0. And again, everything after that is 0. Now, this would be my dv, okay? So this is my u column, and this is my dv column, if you want to think of it that way. So this is my dv, so you need to integrate, right, in the very first step of integration by parts, you would integrate sine x. So the integral of sine x is minus cosine x. And if you did the integration by parts again, that would be your dv, so what would v be? It would be negative sine x. When you integrate again, you're going to get cosine x. And you integrate again, you'll get sine x. Notice I've gone back around. I don't really need the last one, but fine, minus cosine x. Okay? Okay, no problem. Now, keep in mind what we have here. This is u and this is dv. Right, this is u and this is dv. That's du and that's v. So you have to be careful. Remember, in the very first iteration of integration by parts, what are you going to have? uv. Well, here's the u, the original u. Where's v? That's dv. V is here. So when you do uv, you have to go, diagonally. It's not across. Be careful, right? So I usually draw little arrows down me, but before I do that, though, you have to realize when you do uv minus the integral of v du, if you did integration by parts again on this one, right, we did that before, you're going to get another uv, I'll just write the bars, uv, minus the integral of another v du, right? But notice what happens to the integral here. Here, right, it's minus the integral, but when you do it again, it's minus here, and minus here becomes a plus. So we have to reflect that changing sign. And if you do it again, right, like I did here and put a box there, you're going to have a minus, a minus, a minus. This would be a minus again. So to reflect that changing sign on the integral, right, just plus, minus, plus, minus, plus, minus. Just alternate. Let's start with plus. Okay? So you have to adjust for parts inside of parts inside of parts. Okay, now again I'm going to think diagonally this way. Oh, I lied. I didn't mean that way. Notice, why do I stop here? Because if you do it again, it's going to be 0 times something, 0 times something, 0 times something. So all the diagonals after that are all going to have a 0, so I don't need them. Okay, so we can just write down the answer now. So it's that times that, plus that times that, plus that times that, plus that times that, plus that times that. So I get minus x to the fourth cosine x plus 4x cubed sine x, because it's a negative and a negative. And then plus 12x squared cosine x minus 24x sine x minus 24 cosine x, don't forget your plus c, minus x squared cosine x plus 4x cubed sine x plus 12x squared cosine x minus 24x sine x plus minus 24 cosine x. And if you wanted to check your answer, which I'm not, take the derivative of this, product rule, product, and then you can do that one on your own. You'll see that a term from here cancels with a term from here, a term from here cancels here, and you just keep going. Okay, so that's tabular method. That's the section on integration by parts.